Okay, so now we get to talk about inverse hyperbolic function. Now, you remember the hyperbolic functions could be represented involving exponential functions, so it only makes sense that the inverse hyperbolic functions can be represented using log functions or natural logs, since the natural log is the inverse of the natural exponential function. So actually I'll just go ahead and tell you that the inverse hyperbolic sine function can be represented by the natural log of the quantity x plus the square root of x squared plus 1. The inverse hyperbolic hyperbolic inverse function for cosine, or the inverse cosh function, is natural log of x plus the square root of x squared minus 1. And for the hyperbolic tangent's inverse, that's 1/2 times the natural log of 1 plus x over 1 minus x. And so if you wanted to graph these on a graphing utility, you could actually graph these natural log functions, the ones on the right here, and you could get a graph, because you might not be able to find the inverse hyperbolic functions on your calculator or graphing utility. But this is what they look like. So this is the inverse hyperbolic sine function. This is the inverse hyperbolic cosine function. This is the inverse hyperbolic tangent function. And I'm listed the domains for you. This is the hyperbolic cosecant, inverse hyperbolic cosecant function is natural log of 1 over x plus the square root of x squared plus 1 over the absolute value of x. And the inverse hyperbolic secant function is natural log of 1 plus the square root of 1 minus x squared all over x. And then finally, the inverse hyperbolic cotangent function is 1/2 times the natural log of x plus 1 over x minus 1. And you can see I've given you the domains and the graphs of those. Now, these are the formulas, and again, you might want to pause the video or take a snapshot of these. But here, these first 3 rows represent formulas for derivatives of inverse hyperbolic functions. And then there's 3 formulas here that lead to integrals that actually lead to functions that are hyperbolic in form. So you can see these 3 results look a little bit like some of the hyperbolic functions that I just mentioned. So anyway, let's just do a few of these. Let's say I want to find the derivative of a hyperbolic, the inverse hyperbolic sine. So let's say that I have the inverse hyperbolic sine of e to the 2x. Well, that's going to be u prime over the square root of u squared plus 1. Well, u prime would be the derivative e to the 2x, so that's going to be 2e to the 2x. And then over the square root of u squared plus 1, well, u squared would be e to the 2x squared, so that would be e to the 4x. So I would have the square root of e to the 4x plus 1 in the denominator. So that one wasn't too bad. Okay, how about the inverse hyperbolic cosecant of natural log of x? So where's that one? That one looks like that would be here, right? Okay, well, now here u is natural log of x, right? So u prime would be 1 over x. So now the formula says we need minus u prime, so I have minus 1 over x in the numerator. And then in the denominator, I have the absolute value of u, so that would be the absolute value of natural log of x, and then times the square root of 1 plus the natural log of x quantity squared. And then you can actually move the x to the denominator here and get minus 1 over x times this absolute value times the square root. And then let's do some integration here. Okay, so let's say we wanted to integrate dx over 4 minus the square root of 4 minus 9x squared. Well, here that would be, a would be 2, so that would be a squared, and this would be 3x quantity squared. So this would be like, if I let u be 3x, then du would be 3dx. So if I multiply the top by 3, the outside by a third, then the top's going to be du. So now I have du over the square root of 4 minus 9x squared. So that's really du over the square root of 2 squared minus u squared. I lost my 1/3, didn't I? Okay, let's see how that affects me. Alright, so du over that. Okay, well, what's the formula for du over the square root of a squared minus u squared? Let's see. Du over the square root of u squared minus a squared, or a squared minus u squared. Let's see. Oh, here it is. Du over the square root of a squared minus u squared is 1 over 2a times the natural log of a plus u over a minus u plus c. So let's see what I did. I did 1 over 2a, so that would be 1 over 2 times 2, which is a fourth. But I forgot to put the 1/3. So actually just change this to 1/12 right here, and we should be okay. Alright, so that really should be 1/12. Alright, now I have the natural log of a plus u over a minus u, right? Isn't that what it says? Natural log of a plus u over a minus u. Well, a is 2, u is 3x, so that's a plus u. There's a minus u, and then plus a constant. So it's going to be 1/12 times this natural log plus a constant. So there we go. Fixed it. Okay, let's see what we have here. Now on the bottom, I can treat e to the x as u. So then I'll have the square root of 1 squared plus u squared, right? And then the derivative of u would be e to the x dx, which is what I have in the numerator. So actually this could be thought of as du over the square root of a squared plus u squared. So let's see if I have that. Du over the square root of a squared plus u squared. So let's see. Okay, well, it's a little bit backwards here, but this right here, the top one, u squared plus a squared, is the same as a squared plus u squared. So I can do that. That's simply going to be the natural log of u plus the square root of u squared plus a squared plus a constant. So I would have the natural log of u, what's u? E to the x, plus the square root of u squared plus a squared, so that would be e to the x quantity squared, so that would be e to the 2x, plus 1 squared, which is 1. So there it is, the natural log of the quantity e to the x plus the square root of e to the 2x plus 1 plus a constant. Okay, let's do one more. Here, on number 3 here, I have dx over the square over x times the square root of 4 minus 9x squared. Now this time I have, if I let u be 3x, du would be 3dx. So I could multiply. What I'm going to do here is a little bit different from what I've done before. See, I need this to be 3dx so that this will be du. Right, so I'll multiply that by 3, but let me show you why I'm going to keep the other 3 on the inside. Okay, if you go back up here, the only one that allows me to do a squared minus u squared is this one, and it has to have u out here, but I didn't have u out here. U was what? U was 3x. I only had x. So basically, if I multiply the top and bottom by 3, then that fixes that. So now this is u, there's du, this is u, and then this will be a squared minus u squared, or if you want to say 2 squared minus u squared. So now I have du over u times the square root of 2 squared minus u squared. And so going back up here using this formula, that's going to be minus 1 over a. So what's a? A is 2, so minus 1/2. and then natural log of a funky fraction. So that's going to be natural log. The top's going to be a plus a square root. So that's going to be a plus a square root. So that's 2 plus a square root. Square root of what? Square root of 2 squared plus u squared. So that would be square root of 2 squared plus u squared. So let's see. Actually, it's going to be minus because I have a minus. So I have the minus. So it's going to be 2 squared minus u squared. And then over the absolute value of u. So I have over the absolute value of u. Now the last step, I'm just going to go ahead and replace u with what it equals, 3x. So I replace u here with 3x, and I get 9x squared there, and replace u with 3x here, and I get absolute value of 3x. So finally, I get minus 1/2 times the natural log of 2 plus the square root of 4 minus 9x squared, all over the absolute value of 3x plus a constant. So you can see these can get rather tricky, but we definitely have some formulas, some more formulas now that will allow us to evaluate integrals. Well, I tried to find an inverse hyperbolic application, and I looked, and on Wikipedia I found this. Attractrix, from the Latin verb trahere, to pull, drag, is the curve along which an object moves under the influence of friction when pulled on a horizontal plane by a line segment attached to a tractor or pulling point that moves at a right angle to the initial line between the object and the puller at an infinitesimal speed. It is therefore called a curve of pursuit, and it was introduced by Claude Perrault in 1670 and later studied by Isaac Newton and Christian Huygens. Okay, so an example of this would be a semi pulling a trailer around a corner at a right angle. Well, this curve here would be the curve that the trailer would make here as we followed the path. So this is my beautiful rendition of a semi-trailer. So this is the curve we would get. And you can model that curve by this formula. Okay, where A is the length of the trailer and X and Y are points along the path. So if the trailer was 20 feet long, then basically you would get a curve like this. Now, I read this too, that this tractrix actually arises in the following problem posed by Leibniz. It says, what is the path of an object starting off with a vertical offset when it is dragged along by a string of constant length being pulled along a straight horizontal line? Well, by associating the object with the dog and the string with a leash and the pull along a horizontal line with the dog's master, the curve has the descriptive name Hund curve or dog curve in German. And Leibniz found the curve using the fact that the axis is an asymptote to the tractrix. So you can see here the axis here, the vertical axis, is an asymptote to that tractrix. So anyway, if you want to study this more, you can study it more, but that's real. I'm sure there are other inverse hyperbolic applications, but all I found when I was looking, I didn't look that hard, but all I found was something like this, where it represents the graph of a tractrix. So anyway, I believe that's all we've got in this chapter. I might have another section I want to throw at you that might involve some other applications, but I'm pretty close to done with this chapter.